Guys, so I just wanted to go over some of the problems that appeared in the Intro to Limits worksheet because there were a few consistent issues that people had. So the first one is exercise 1, the very last problem here. So here's the graph of our function f, and I'm asking you to find the limit of this function as x approaches 0. Now, the first thing that you should notice when you see this is that unlike many of the other limits appearing in this problem, there is no plus or minus above the 0, right? There's no plus or minus sitting above this 0 here, unlike over here there's a plus or elsewhere there's a minus. That means that this is a two-sided limit, right? And a two-sided limit is only defined if the left and right hand limits agree, that is, if they're equal. So to determine whether this thing is even defined, we have to consider both the left and the right hand limits and ask, are they the same or not? So let's look at the graph and see what's happening near x equals 0. If I go over to the graph, 0 is right here. If I approach 0 from the left, then the value of the function is approaching 3. If I approach 0 from the left, then as that happens, the value of the function is approaching 3. Okay, so the left-hand limit is 3. What about the right-hand limit? Well, as I approach 0 from the right, the value of the function is approaching 3 also. And so because the left and right hand limits are both 3, the two-sided limit does exist. And in fact, it's just equal to 3. A lot of people said that this thing was undefined. It's perfectly well defined. It's 3. I think that what a lot of people did maybe was they said, there's nothing strange happening at this part of the graph, so I guess that's just undefined. As I mentioned in the notes earlier in the worksheet, it's important to recognize that we can ask questions about limits even at places where the graph is perfectly well defined and well behaved. What I mean by that is the following. It is true that most of the time when we ask you a limits question, it will be a question about an x value at which something strange is happening. Looking at this graph, obviously I'm going to ask you about -1 because all kinds of crazy stuff is happening at -1. And obviously I'm going to ask you about 1, and obviously I'm going to ask you about 3. But it is important to understand that we can ask limit type questions even at places where nothing unusual is happening at all. Nothing unusual is happening at all at 0. The function is perfectly well behaved here. And yet I can still ask you what is the limit as x approaches 0. It's not a very interesting question, but it's still a question I can ask, right? So understand that everything that we've talked about with regard to limits applies to perfectly ordinary points in the graph, not just places where something strange is happening. I think that what a lot of people probably did is they looked and they said, nothing weird is happening at 0, so I guess that's undefined. No, that's not true. Moving on, the next thing I wanted to talk about was exercise 4. Pretty much everybody recognized that the other discontinuities which needed to be noticed were, so the very first discontinuity, of course, happens at x equals -2. Everybody got that. The next one happens at x equals 0, and you had to fill that in. So let's look at what's happening at x equals 0. And if you remember, I had you determine whether, properties 1, 2, or 3 from here held for each of those discontinuities. So let's have a look at 0 and see which of these statements holds and which one is true, because people really were confused and didn't give the right answers on this. So these three properties, are, if you remember, are what is necessary for the function to be continuous at the point. Now you can obviously tell the function's not continuous at 0. There's a gap in the graph, but the point of this exercise is to see exactly why It's not continuous. Remember, being continuous means that this equation holds. This equation is true. And in order for this equation to be true, in order for the function to be continuous at that point, these three things must hold true. Okay? And because there's a break here in the graph, because this function is obviously discontinuous at 0, one of these three things has to fail. At least one. Maybe many of them fail, right? And your job is to figure out which ones fail. So let's see. Which ones fail and which ones hold? 1. The first half of the equation, limit as x approaches c, that's this thing right here, must be defined. Since limit as x approaches c is a two-handed limit, this means the left and right hand limits must be equal. A lot of people said that doesn't hold at x equals 0. A lot of people said that fails at x equals 0. No, it doesn't. This holds. This is true. Okay? The two-sided limit is defined at 0. It is defined at 0 because as you approach 0 from the left, you get -1, and as you approach 0 from the right, you also get -1. Because the left and right hand limits are equal, the two-sided limit is defined. Okay? The two-sided limit is defined. So that first property holds. The second property is that the second half of the equation, f of c, must also be defined. In other words, the function must be defined at the point. In other words, the function must be defined at 0. Well, is the function defined at 0? A lot of people said no, but it is. The being defined at 0 simply means that the function has a value at 0. Does the function have a value at 0? Yes, it's whatever this y value is. It's maybe 0.5 or something. The function is defined at 0. Sure, it's not continuous at 0, but it is defined there. You can evaluate the function at 0. It's 0.5. Okay, so the second condition holds as well. And yet the function is not continuous. And the reason for that is that property 3 fails. Property 3 is that even if both halves of the equation are defined, in other words, even if the two-sided limit is defined and the value of the function is defined at the point, these two things might not be equal. And that's what's happening here. The two-sided limit is defined. It's -1. The value of the function itself is defined at the point. It's 0.5. But those two things are not the same. -1 is different from 0.5, therefore not continuous. Okay. The other discontinuity was at, the next one would be at x equals 2. Okay, and again, people sort of mixed this up. Let's go through the properties. Does property 1 hold? Property 1, if you remember, is that the two-sided limit is defined. Is the two-sided limit defined at 2? Yes, because as you approach from the left, you get -1, and as you approach from the right, you also get -1. Since those two things are the same, the two-sided limit is defined, and it's -1. So that property holds. Property 2. Property 2 simply says the function has to be defined at the point. Well, is the function defined at the point? Does the function have a value at 2? The answer is no. There is no black dot anywhere sitting above 2, okay? So the function is not defined at 2, so therefore this thing fails, which means, if you remember, the third property fails automatically. Okay, so that's exercise 2. Let's move on now, finally, to the sketching exercise, okay? A lot of people did something rather strange. People, by and large, understood what each of these properties meant. However, what I saw in so many graphs was the following, and I left a comment on your graph if you did this. What so many people did was they drew different pieces on top of each other. Okay, they drew different pieces of the graph floating above one another. This is not allowed. What I'm talking about is something like this. if you notice here, I've made a graph. This graph doesn't satisfy any of the properties here. I'm just showing you what I mean when I say pieces floating on top of each other. If you look at this graph here, I've got this piece here, and it's floating above this other piece here, and then this piece here is floating above this other piece here. This is not allowed when you're drawing a function. Why not? Because if you remember, there's something called the vertical line test. You learned it maybe, I don't know, last year or middle school or something, but it tells you it's a condition for when a graph represents a function, okay? This graph, whatever it represents, does not represent a function because it doesn't pass the vertical line test. What that means is that you can draw vertical lines which cross the graph in more than one location. For example, this vertical line right here crosses the graph once, twice. Okay, so this graph fails the vertical line test. What that means is it doesn't represent a function. Because remember, a function is supposed to have only one output for every input. I could ask you, what is the value of the function at 0? What is f of 0? Well, it seems like there's two possible answers. It could be 2 if you use this piece, or it could be whatever this y value is, negative 0.3 or something, right? So functions for each input are only supposed to have one output, but this thing, whatever it represents, seems to have two different outputs for the same input 0, and that's bad news, right? So you have to do this without having overlapping pieces, okay? I constructed one possible way of doing this. There are many different ways of doing it. You can satisfy all the properties and draw it quite differently, and some people did, but this is the way that I chose to do it. And if you take a look at this and compare it with each of the properties 1 through 9, you'll see that it satisfies all of them. Furthermore, you'll notice that it passes the vertical line test everywhere. Maybe you're saying, oh, but look at this. Don't these two pieces overlap? No, they don't, because this is a full circle and that's an empty circle. If I asked you what is the value of the function at 2, there's not two outputs for that. There's only one. It's this one. The value of the function at 2 is 1 and not -1. That's the meaning of these full and empty circles. Likewise at 4, if I asked you what's the value of the function at 4, there's no ambiguity. It's -3 and not this value here. That's what the full circle and empty circle tell you. They tell you what the value of the function is at 4. So this thing does pass the vertical line test. There are no overlapping pieces, so it does represent a function. Okay, so hopefully that clears up some of the confusion around these problems. It is kind of a subtle business, and it is a little bit easy to get lost in the definitions, but a lot of this stuff is you really got to understand the definitions carefully. You have to be very careful in your thinking. And so I just recommend that you be careful, okay, when you're doing these kinds of problems. Hope you all are